Okay, hi everyone. My name is Solomon, and today I will be giving a talk on synthesizing quotient lenses. So here's the big picture. In 2005, Nate Foster, among others at Penn, introduced the programming languages community to lenses. So what is a lens? Well, our previous two talks have gone over this, but in plain terms, a lens is a program that can be run in two directions, so mapping inputs to outputs and outputs to inputs. And there are various kinds of lenses. So in the previous talk, we saw the one I call classical asymmetric lenses. So these are the ones introduced by Nate Foster originally. But there are various kinds of lenses, and each of these classes of lenses comes with their own set of guarantees. So, for example, the set of or I should say, the class of bijections between sets forms a class of lenses, since every bijection can be defined by two functions which are mutual inverses of each other, and this is a guarantee that the class of bijective lenses gives. So. As of now, usually lenses are defined using combinators in domain-specific languages. And as some of you can attest, programming using combinators can be a challenging task. So in this year in Popol, we presented a synthesis tool for synthesizing bijections, or I should say a specific class of bijections between regular languages. And this was great. But transformations in the real world are not always bijective. So, for example, if you're considering a transformation that maps between data in JSON formats and XML formats, you may define, or you may wish to define the same behavior for two JSON records if they differ on the order of fields, for example. So in this case, the transformation will not be a bijection, and we cannot synthesize these. And the upshot is that in this talk, I will talk about a tool that we developed for synthesizing bijections between equivalence classes. And this is the big picture. So in a little bit more detail, as I said before, in our work, we're interested in synthesizing lenses. So an example of this is a lens or a bidirectional transformation which transforms data in JSON format to data in XML format. So on the JSON side, we have just the full name and the year of birth. On the XML side, we have last name followed by first name followed by year. And as of now, we can synthesize, or I should say, as of before ICFP, we could synthesize this transformation. And more generally, we can synthesize a class of bijections between regular languages. But again, as I mentioned, sorry, wrong slide. But anyway, so in more detail, the way this synthesis tool works is the programmer provides a source regular expression and a target regular expression, as well as a set of examples, and provides this to the synthesis tool, which we call optician. And if the synthesis task succeeds, then we get a program P, which is a bijection between data described by the source regular expression and the target regular expression. And the synthesized bijection is guaranteed to satisfy the set of examples. So, like I said before, the problem is that representations are not always unique. So, for example, on the JSON side, we might have, the format might allow for us to have arbitrary occurrences of white space between the two fields. And on the XML side, we might have an even more complicated equivalence relation. So we may allow arbitrary occurrences of white space to occur between the three fields. And moreover, we may even wish to ignore the order of fields. So if you look at the first XML file, we have the last name followed by the first name followed by the year. But then in the second one, we have the first name followed by the last name, then the year. And as I said, the upshot is that we want to synthesize bijections on equivalence classes, and that's the content of this talk. So the way that our synthesis tool for quotient lenses works is the programmer specifies the source equivalence relation and the target equivalence relation and provides a set of examples. And if the synthesis task succeeds, then we get a bijection between the equivalence classes that satisfies the examples. So this is the content of our talk. And so the plan for the rest of the talk is that, well, the first thing is that the goal is to synthesize bijection between equivalence classes. And to do this, I will first talk about how we specified equivalence relations on regular languages using what we call quotient regular expressions. So this is one of the contributions of our work. After explaining this, I will go over the synthesis algorithm, and then in the last part of the talk, I will argue that synthesis is fast and leads to less code. Okay, so our idea for this work was a very simple one, which is we synthesize bijections with canonizers at the edges. So what does this mean? Let's say that we start with a JSON equivalence class. What we simply map that equivalence class to a canonical representative. We apply the forward transformation of the synthesized bijection, and then we get a canonical representative of an XML equivalence class. And then we simply include the canonical representative in the equivalence class. And similarly in reverse, so simple idea. But there are two main challenges which we encounter when we do this. So the first one is, if you recall, I said that we want the programmer to provide a specification of the two equivalence relations on the source and target side. So the question is, well, how do we specify equivalence relations? And as I mentioned earlier, our solution to this was to introduce what we call quotient regular expressions. And a quotient regular expression, or a QRE, is simply a regular expression with lightweight annotations that mark inessential details. So if we go back to the XML equivalence relation which I just described, this is the QRE that we would use to specify this equivalence relation. So there were two equivalences that I described. The first was permuting or ignoring the order of fields. And the way that we do that with QREs is we just have this combinator called perm for permute that just says ignore the order of fields. And then for the white space, we just say collapse arbitrary occurrences of white space to a single new line character. And so these QREs define equivalence relations because if we were to write out what the whole equivalence relation is for the data, the equivalence class, we have at least six different six different regular expressions, one for each permutation of the fields. But now with just this one expression, permute last first year with collapse, blah, 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 we only need to write this thing once and we get an equivalence relation. So in a little bit more detail, the denotation of a quotient regular expression has three parts. There's the whole language, which is a set of all strings being quotiented. There's the kernel language, which is a set of canonical representatives. And then there's a canonizing function, which sends each string in the whole language to its representative in the kernel. And two strings in the whole language are considered equivalent if they map to the same canonical representative. So this was our solution to the first challenge. How do we specify equivalence relations with QREs? Okay, so going back, as I said, we want to synthesize bijections with canonizers at the edges. So now we have a way of specifying the canonizers at the edges. And the next step is simple. We plug in a synthesized bijection in the middle. But this is not the whole story. So if we have two of these lenses, these quotient lenses, we want to define combinators on them. So for example, if we have a lens from S to T and then another lens from T to U, we want to be able to define the composition of those two lenses that goes from S to U. We want to be able to synthesize concatenations, or if you want to, another way to say this is we want to synthesize lenses on product types. So if we have a lens from a source S1 to a target T1, we have another lens from S2 to T2, we want to be able to define the lens which, given a pair S1, S2, gives us back a pair T1, T2. We want to synthesize unions. So if we have a lens from S1 to T1 and then a lens from S2 to T2, we want to be able to say, for example, if I give you an S1, then use the first lens in the forward direction, and if I give you a T2, use the second lens in the backward direction. So this is lenses on sum types. And we want to define iterations. So another way of saying this is we want to define lenses on lists. So if we have a lens from S to T, we want to be able to define a lens which, given a list of S's, gives us back a list of T's. So as I said, we can synthesize the lenses on the left from QREs. We simply compute the kernels on each side and then synthesize a bijection between the kernels. So that's easy. But if we look at the right-hand side, well, in plain language, things on the right-hand side don't look like things on the left-hand side. So can we remove these things in here, so the combinators? Or if that does not make sense, another way of saying this is, can we convert each one of these things to one of these? So why do we want to do this? So if we can convert each of these complicated things to one of these more simple things, then we don't have to synthesize complicated things. We can synthesize simple things, since each complicated thing is simple. And that sentence might not make sense, but okay. Okay, so the question was, can we convert each one of these to one of this? And simply put, yes. And this is and this is something we discussed in the paper, and I will not say too much more about this. Okay, so the synthesis algorithm proceeds as follows. We simply start with two QREs. We compute the kernels for each of the QREs. We feed the kernels to optician. We get a bijection between the two kernels. We apply QREs to the bijection, and then we get a quotient lens. And that is that. So on to evaluation. So we evaluated our implementation in two different ways. So we were interested in two metrics. Number one, does synthesizing lenses from QREs lead to less code? And second, is QRE synthesis, or does synthesizing lenses between QRE, is that feasible? So for the first question, the question on code size. So on this graph, we have the number of AST nodes produced by each of three programs for each of 10 different benchmarks. So on the x-axis, we have 10 benchmarks, and for each of those benchmarks, we produce 3 different programs. And on the y-axis, we have the number of AST nodes produced by each of those programs. And for this graph, lower is better. So we want fewer AST nodes, since fewer AST nodes means a smaller program. And we want to have smaller programs. This is one of the challenges with programming with combinators. We oftentimes have big programs that are very easy to mess up. So how did we, one of these 3 programs that I am talking about. So the first kind of program is a program that is basically written just by hand, no synthesis. So that's the blue graphs. The second graph are the ones in green. So in this case, we write the whole regular expression, so the whole format, and we write the canonized function by hand, but we're allowed to synthesize by ejection between the kernels. And then in the last kind of program is quotient synthesis. So we write QREs by hand and synthesize lenses between QREs. And what we find is that for each of these benchmarks, not synthesizing anything leads to more AST nodes. Using a little bit of synthesis, or using a lot of synthesis, but writing canonizers and whole formats by hand leads to less code, but still a lot of code. And then in quotient synthesis, where we write just the QREs, but then synthesize the lens between QREs, we get the least amount of code. And I should say that these benchmarks are from the original optician benchmark suite. So when we were performing the evaluation in that paper, we slightly cheated a bit by modifying the formats so that they would be bijective in nature. We bijectified the formats. But with this work, we don't need to do that because we have quotient regular expressions, which are more expressive specifications. So the language of QREs is more expressive than just normal regular expressions. So this is an added advantage of these QREs. And if you're interested in, or if you're wondering where did these benchmarks come from, they came from FlashFill, which is an Excel autocomplete tool. They came from Augeus, which is a tool for editing Linux configuration files, and some of them are custom benchmarks. So lens synthesis leads to less code. And then finally, we were interested in performance. So how does quotient optician perform relative to normal optician? So on this graph, on the x-axis, we have amount of time. On the y-axis, number of benchmarks completed, and higher is better. So we want more benchmarks completed in a small amount of time. And we found that quotient optician is not significantly slower than normal optician. So this overhead of computing kernels and canonizers is not restrictively expensive. So in summary, our goal was to synthesize bijections between equivalence classes. We specified equivalence relations using QREs. I explained the synthesis algorithm and argued that synthesis is fast and leads to less code. And that's the end of my talk. Thanks.
All right, Solomon, thanks. We've seen a few questions come in. One of the first one is what you're doing is, of course, synthesizing lenses. And do you have any idea of how easy or how hard it is for programmers to tell whether the lens that you've managed to synthesize is the one that they were interested in?
Yeah, so this is where the examples help a lot. So if you want a lens of a certain type, so a lens that maps between 2 formats, there could be multiple lenses, and the programmer kind of has the onus on them to provide the examples that guide the synthesis task. So that's my answer to that question.
Okay. There's a few questions about QRE. So besides perm and collapse, do you have any other primitives?
Yes, we have a few other primitives. Uh, and I mean, QREs are basically meant to be used like regular expressions. So I guess we can also compose, concatenate, iterate them.
Yeah.
But we have a few other combinators.
And what drove your choice to use QREs rather than other kind of regular tree languages or, yeah?
Yeah, so, well, we wanted a specification language that is kind of like regular expressions. So with QREs, you only add lightweight annotation. So you're basically writing regular expressions and a little bit more, but not too much more. So we wanted a specification language that is easy to use for programmers.
And the other kind of tree query languages are not easy to use?
I don't know how to answer this question other than to say
Fair enough.
QREs are lightweight.
Okay. Fair enough. You can sleep on it. So there was another question which I'm trying to find. Oh, sorry. Oh yeah, that was it. So
Okay.
what you're doing is, to handle the quotienting, is you start by collapsing or kind of manipulating your input and then making it canonical in some way. And there's a question which what I found interesting was, have you thought about recording the changes that you made to make it to find this canonical representation so that you might be able to reverse them back? So if you, for example, get rid of white space, that you remember where you stripped off the white space, then you can then do all your lens magic and then maybe reapply those changes as well. To choose a member of the equivalence class which is most closely related to the kind of original one.
So we did not think about this. So for each equivalence class, we have just one canonical representative.
Sure.
So you're asking for if I'm given members of an equivalence class, we want to produce we have not just a single canonical representative, but maybe several.
No, it's not so much about the canonical representatives, but the way I understand the question at least, is that what you do is you map down to the canonical one and then you do all the lens magic. Whereas maybe what you might want to do is, as you map down, that you remember kind of the changes that you made, so that after you've done all your lens updates and things, that you try to kind of reconstruct something which is in the same equivalence class, but somehow very similar to the original input.
Yes, I think this would have been a good idea for our work, but I guess we did not think about this. Okay. So we simply guarantee, or we only guarantee that the bijection is between equivalence classes. But yeah, that idea does sound like a good idea. I guess we didn't think about this.
Okay. Well, you have some future work. So thanks, Solomon, again.